All right, good afternoon, everyone. So how are you doing today? I hope you're refreshed from last week, right? So I hope you had a good weekend. So now we're back to or we should be back to our academic selves, right? So another topic for this afternoon. So still I'll be discussing some things from linear algebra, which in one point or another in your data science life will pop up and will be used, because even though we said data science is just full of black boxes that you'll just need your data, pre-process it, and then feed it into your computers, into your algorithms, into your models, and then you're gonna get some useful results, or you will get some insights, etc. Right? It's still very handy to know basic mathematical tools that you can use to tweak whatever algorithm or whatever whatever modeling process or procedure you are implementing. All right. So last time we talked about LU factorization and how they can help us in solving linear systems, specifically those large linear systems for which computing the inverse of the coefficient matrix is quite difficult to do. And what else? For those large systems that you have to solve iteratively over and over again, right? Especially if you have a very huge matrix A, and then the right-hand side, the vector of constants, should be computed iteratively, or you don't have access to all of the possible right-hand side. So essentially, computing the inverse of the matrix is quite difficult. And number two, it will also be difficult or it will be impossible to perform a parallelized version of the Gauss-Jordan algorithm or the Gaussian elimination procedure. That's why you need to perform them in series, or we are forced to do them in series, right? But if you can factorize your matrix, say in a lower and upper triangular into lower and upper triangular factors, then you only need to do a combo of the forward substitution and the back substitution to complete the process. All right. Now, one problem with that procedure is that procedure, though, can be extended for rectangular matrices. That's not often easy to do, or the resulting system or the resulting system with an upper triangular or a lower triangular coefficient matrix is still difficult to solve, or there would be some numerical instabilities that might occur whenever you're performing it on machines. A more stable version or a more stable factorization method is what we call the QR factorization. Oh, by the way, remember also that not all matrices admits an LU decomposition, meaning when I say LU decomposition or LU factorization, there's no need for the use of preconditioners or permutation matrices, right? Now, so those are the drawbacks of the LU factorization. While what we'll talk about today is QR factorization, which is basically you still factorize your matrix, but this time with a different form or a different in a different way, such that number one, we will see that this is more computationally stable. It is really related to how you solve least squares problems, which are very abundant in data science. And then what else? A nice property of the QR factorization, any complex matrix or matrix with complex entries admits a QR decomposition. Although, just a caveat, uh, the uh, the machine implementation of QR factorization are still prone to numerical instability. So we need to be very careful which algorithm we use for the QR factorization. And yeah, and still, after we do the QR factorization or decomposition, we can just do forward or backward substitution, whichever is the case. All right. Now, even though the QR factorization is tied to a very famous linear algebra algorithm, which is the Gram-Schmidt process, I won't assume that you know the Gram-Schmidt process. Although, can I have a show of hands who are who among you are familiar with the Gram-Schmidt process? If you still remember your linear algebra. Okay, thank you, Jihan. Okay. I think Z is also good. Lynette's also good. Christian already forgot it or never never encountered it. So that's fine. I'll be skipping a lot of this module because this module was prepared for my PhD class in the UP Open University about linear algebra. So that's why it's a little bit on the theoretical side. But what I'll highlight here would be basically how you perform the QR factorization, or at least an algorithm to perform the QR decomposition that will require less linear algebra topics like the Gram-Schmidt process. I'll totally skip the Gram-Schmidt process. And number two, this would be the algorithm that is more numerically stable. Because remember, whenever doing something in a computer, you always have to contend with two things. Number one, the theoretical error, right? The theoretical error, which is the error that is inherent in the approximation process you use to design the method, right? So you have an exact problem, like say, for instance, a differential equation or an integral equation. Now you need some approximative way to solve the problem. So you devise some numerical schemes. So on paper, you are losing some accuracy because of the approximation method that you design. So that's essentially inherent in the process itself. That's theoretical error. But once you employ the numerical method in a computer, you again incur another type of error, which is the machine error, or the error due to machine precision or machine calculations. Remember, computers are finite machines, so they can only accommodate a finite number of numbers. So if you have pi, incidentally, today is Pi Day, the International Day of Math, right? It's an irrational number, a never-ending, non-terminating, non-repeating decimal number, right? So, but inside a computer, it cannot admit all of the values, all the digits in pi. So it will just say store pi is 3.1415.92654. And that truncation, all the truncated decimal digits, which occurs at the or towards the end of the number, might matter, and all of those truncations might pile up. So we need to be careful in designing the numerical implementation of the procedure so that we minimize the effect of machine truncation in our solution. All right. So that's why I will just choose the best QR factorization, or the best basic QR factorization algorithm. So if you downloaded the handout on the QR factorization I have on our website, you can just skip right ahead to page 21, all right, which is the page on your screens. So essentially, again, it's a matrix factorization procedure. So I want to find ways on writing the matrix A as a product of two matrices. This time, I'll call the matrices Q and R. Now, one big difference with the LU factorization we talked about last time is that we are starting with an input matrix A that we wish to factorize, which is rectangular in nature, right? So it's an M by N matrix with possibly complex coefficients. But again, since this is not a hardcore math course, so we can limit our discussion to the set of real numbers. So you have a matrix consisting of M rows and N columns with real numbers as entries. And a QR decomposition of the matrix A is writing A as a product of matrices Q and R. Well, what are the matrices Q and R? The matrix Q is a square matrix with the same number of rows as your input matrix A, so it should be M by M, and it is unitary. When we say unitary, so it is a matrix such that its inverse is its conjugate transpose, right? Or in other words, since we are limiting our discussions to matrices of real entries, so basically we will be saying that if this is replaced by R, we will have Q inverse equals the transpose of the matrix Q. All right, so that's why this is quite important, or this is quite powerful, because I have a guest here. Sir Jomar is here in the lecture hall. But anyway, yeah. So the idea is we are getting rid of the tedious process of matrix inversion, because essentially I am choosing my first factor to be a matrix whose inverse can be computed, actually not even numerically computed, it could be lexicographically computed, because the inverse of the matrix Q is just the transpose uh, of the matrix Q itself, right? For those who forgot, if your matrix is, hold on. Yeah, I always assume that you still remember your linear algebra, but just in case I forget to define some terms that you are not familiar with, just let me know, right? So if you have a matrix A and the matrix has entries A, I, J, meaning it has the number A sub ij, it is the entry on the ith row and on the jth column, all right? Its transpose is the same, is the matrix A to the T, so it's A transpose, wherein the row number and the column number of each of the entries are interchanged. So that means the entry on the matrix A on row I and column J is now put on the jth row and the ith column. Right? So you're switching the row number and the column number of your original matrix. Uh, Now, if you're curious about the conjugate transpose, which is A star, basically it is AJI. So you take the transpose of your matrix A, but you get the conjugate of all the entries. Remember the conjugate of a complex number Z. If your complex number Z is A plus BI, its conjugate is Z bar, which is A minus BI. All right. So I hope these are ringing some bells from your elementary algebra or your linear algebra classes. All right. So you see, now the process of the matrix inversion is a little bit taken out of the equation because we are cooking up our factorization so that we don't need to go through the very expensive process of computing the inverse of the matrix, which will be involved in our factorization scheme, right? Because again, the matrix Q was chosen purposely to be a matrix whose inverse is already known, all right? It's unitary, so that means the inverse of the matrix Q will be its transpose, or in case of complex entries, its conjugate transpose, all right? Oh, by the way, Jehan is asking where can they get a soft copy of the lecture today? It's available on our AMAT 255 website, uh, Unit 2B, and you look at the lecture notes on QR factorization, right? So if it's not there, just let me know, all right? So that's our goal. Oh, sorry, that's our goal for the matrix Q. Next, the matrix R is also special. The matrix R is a rectangular matrix of the same size as our matrix A, but it is upper right triangular. So it's a special case of an upper triangular matrix. We don't require it to be square, all right? But the idea now is still the same. You might have a very tall and short matrix, right? Then your main diagonal is over here, all right? And it would be a right upper triangular if all entries below the main diagonal are all zeros, right? You might have non-zero entries here, that's fine, but everything below the main diagonal will still be zero. Okay, all good so far? I hope it is. This is quite of a scare whenever students are not responding to questions because there are two possibilities. Number one, the topic is so clear that you don't have any questions at all. Or number two, the lesson is very unclear that you cannot formulate a sensible question, all right? So I hope it's the former, right? So this is something that I was telling you earlier, Theorem 43, that every matrix has a QR factorization. And it is not just any invertible matrix, it is not just square matrices, but all matrices admit a QR factorization, right? So that leaves some of the major questions because in the LU factorization, we don't want to do LU factorization if we know that there is no LU factorization, because essentially we might be wasting some computational resources. the beauty of QR factorization, we are guaranteed that every matrix will have a QR factorization. I will not show the proof. It is quite constructive and it makes use of the Gram-Schmidt process. All right. But essentially, let's just keep this in mind. I won't ask you to prove it either because it's a data science course. This is a linear algebra thing, but it's a nice guarantee, right? Okay. Now, the notes have some algorithms for the QR factorization, but I want to focus on what we call the householder algorithm, which is algorithm number 3 on the notes. Okay, so you can skip after those introductory pages to page 23. All right, and this gives us a procedure on how to do an LU factorization. A QR factorization of a matrix A. Right. So this will be quite computational, and during your free times, you can try to write a short program for the QR factorization. I don't know if I have a screenshot of my program here, but I don't think it's very hard to do. So it's just a couple of for loops, and then you'll be good, right? Now this is called the householder QR factorization. Other QR factorization algorithms would be the classical Gram-Schmidt QR factorization, the modified Gram-Schmidt factorization. But the problem with the classical Gram-Schmidt factorization, it is very prone to truncation errors and numerical instabilities. If you will be performing, I think I have 2 or 3 algorithms for the QR factorization here. If you'll be performing everything by hand, then they will give you the same answers, right? But once you employ them in computers, truncation errors will affect mostly the results from the classical Gram-Schmidt process, right? That's why even in linear algebra, in your classes there, you might have discussed the classical Gram-Schmidt process, so that's fine. But whenever you'll be performing computations involving the Gram-Schmidt process in a computer, you should not use the classical Gram-Schmidt procedure because the truncations in the computers will ruin all your results, right? So it will not be accurate. So if you want to investigate that a little further, you can read some parts of this module. I have a short examples about them. So, but it's really apparent that you need a modification for the Gram-Schmidt process for it to be apt or suitable for machine implementation, right? Now, in this algorithm, in algorithm 3, I'm employing some MATLAB terminologies or MATLAB notations. So remember, we'll be starting with a rectangular matrix A. Now, if I want to get just the submatrix of that matrix A, this will be my notation. This will be my notation, right? So whenever I write A of, then there are 2 numbers or 2 sets of numbers separated by commas inside the parentheses. So this is just the submatrix of the matrix A consisting of rows from number I to number I prime and consisting of columns from J until J prime. So these are semicolons. I hope you can read my handwriting. I already have a typewritten form for this, but I haven't proofread them yet. So because I asked my intern to type it for me. But anyway, so in the meantime, let's use this. Just let me know if something is not readable. I also discovered some grammatical errors here, so just pardon me for those. Right? I think I am writing this in the wee hours of the morning, so there are inconsistencies here, but the gist of the topics are the same, right? So for instance, if I write A of 3 to 5 and then 1 to 8, all right? 1 colon 8. So this is the matrix A, but I will only retain the 3rd to the 5th row and the 1st to the 8th column. And then I'll erase everything else, right? So that means this matrix is, what would be the size of this matrix? So I'll have rows 3, 4, and 5. So we'll have 3 rows in all, and then we'll have 8 columns. So this will just be the 3 by 8 matrix coming from A, where we only retain the 3rd to the 5th rows and the 1st to the 8th columns. Okay. Is that notation clear? Because this will appear several times in algorithm tree. Okay. If I want to get all of the rows, instead of putting 1 to the maximum number of rows, I'll just put a colon. So if you see a colon here, it is the matrix A where I retain all the rows, but only the jth to the j prime columns. All right. Similarly, I can put a semicolon on the column side, or the space for the column number. This means I'm just getting the matrix A, or the part of the matrix A, starting from the ith row to the ith prime column. I prime sorry, from the ith row to the I prime row, and I'm retaining all the columns. Okay, all good? Right. I'll have a specific example later so we can take a look at it, all right? So algorithm tree. So again, we start with an M by N matrix, a rectangular matrix A consisting of complex entries, all right? Or for our case, you can also just look at we can look at real entries. Then the output would be the unitary matrix Q. Again, when we say unitary, Q inverse is equal to Q transpose, or Q conjugate transpose, and the right upper triangular matrix R, which is the same size as our matrix A, but it is right upper triangular. Okay. And here's the algorithm. We will iterate around the variable K, the dummy variable K will start from 1 to the column number, right? So the number of iterations in this for loop would be equal to the number of columns of your matrix A, right? And then for each of the column numbers, starting from 1 until n, here are the steps that we're going to do. Number 1, I will let y to be this guy, right? So remember, this is the matrix A where I keep only the kth to the mth row. But remember, m is the total number of rows in the matrix A. So I will erase the first to the k minus first rows, and I'll retain everything. But I'll only get the kth column. So essentially, this matrix here, or this matrix Y here, is actually of dimensions what? It's a matrix with how many rows and how many columns? For sure, this only has one column, right? Because I'm only keeping the kth column. What do you think is the number of rows? I'm keeping the k to the mth row. Any guesses? Actually, it's not a big deal once we write it in a computer, or if you're using MATLAB, you simply type exactly this. That's why I chose this to be the notations in my lecture notes, right? It's going to be m minus k is Jahan's guess. I think that's close, but not quite. It should be what? N minus m, nice try Z. But I don't think that's the answer. Can we verify, or can you verify that it should be m minus k plus 1? Right, so whenever doing like this, you can start with specific values for k. Remember, k iterates from 1 to n, right? So for instance, when k is equal to 1, you're taking a first to the mth row, followed by 1, all right? So you're just taking the first column of A, but you're taking the first to the mth row. So there's a total of m rows, right? You're keeping the first to the mth row. So in that case, this has m rows. Will my formula give me that? K is equal to 1? Yes, m minus 1 plus 1. So I'm good, m by 1. When k is equal to 2, on the second iteration, once you completed all the steps inside this for loop, you're going to go k equals 2. When k is equal to 2, this would be your submatrix. This would be your vector y, or your matrix y. It will be 2 colon m, comma 2, right? So that means you're keeping the second to the mth row, and then just the second column, right? So you only have one column, the second column, but you have m minus 1 rows, right? Because you're dealing with the second to the m row, to the mth row, right? And when k is equal to 2, this will be 2. So I'll have m minus 1, which is right, okay? So I think this is the right dimension. So y is always a vector, okay? The thing about this householder QR factorization, we are updating uh, one row and one column at a time. And once we have updated that row and that column, they are fixed. So we are not dealing with them again. Look at this. The first iteration will update the first row and the first column. And in the next iteration of the QR factorization, we'll just be dealing with the second row, with the second to the mth row and the second column. We are leaving behind the first row and the first column because they were all already updated during the first iteration, right? So that's why Householder's algorithm is, I wrote that here, it is an orthogonal triangularization of the matrix A. Because our output here is a triangular matrix. And then while we triangularize the matrix, we are orthogonalizing it as we go along. Okay, so that's the first step. So you get you get the vector y, right? So the vector y, which we will use in the updates, and we will let y sub 1 to be the first entry. Remember, this is the vector y will look like this. Y1 will be the first entry there. So that's going to be our y1. Okay, so you just save it, whatever that y1 is. And then right after that, the second step is to compute the vector w. The vector w, or two vectors actually, the vectors w and the vector v sub k, right? But they are really related to each other because you will see that the vector v sub k is simply the unit vector in the direction of w, right? So how do you compute w? Just follow this formula. It is the matrix, it is the vector y from step number 1 plus sine y sub 1 is just whatever the sign of y sub 1 is. It is positive 1 if y1 is positive. It's negative 1 if y1 is negative, right? So it's plus or minus 1 depending on the sign of y sub 1. And then this is called the L2 norm of y2. But the L2 norm of y2 is basically the square root of the sum of the squares of the entries of y. 1, 2. What is its dimension? M minus k plus 1. Are you all familiar with the L2 norm of a vector? You still remember it from your courses, right? So you just simply take the square of all of the entries of your vector, sum them up, then take the square root of the sum. That's our L2 norm. Times E sub 1. E sub 1 is the first elementary vector of the appropriate size. Okay, so all right. So now when I say E sub 1, this will just be the vector of the right dimension or the same direction as y, but it has 1 on the first entry and 0 elsewhere, right? Okay. So again, let's see, what should be the size of E1? Well, again, what's the size of y? Y is an m minus k plus 1 by 1 vector. So that means E1 is the vector of the same size, so it should have m minus k plus 1 rows. All are zeros except the first entry. All right, so that's what E sub 1 is. That's what we mean by the first elementary vector. Okay. And then once you compute W, all right, so you'll just put it in your program, in your code, then you need to take its unit equivalent, right? So the unit vector representing W. So you simply multiply W by the reciprocal of the length of W, right? So vector W times 1 over the norm of W sub of W. Okay. so that the norm of V sub k is now equal to 1. So it's a unit vector in the direction of W. Okay? So highly computational, there are nice geometric interpretations for this. But again, we're not interested with that in this course. So let's skip ahead and let's just appreciate them as steps necessary to compute the QR factorization. Okay. Now, this was my promise earlier that at every step of the way, we will be updating the appropriate entries of the matrix A. We'll be leaving behind all those that we have already updated before. Remember, on the kth iteration, we are assuming that the first until the k minus first rows and columns are all good, right? So at this step, I'm going to update the kth to the mth row and the kth to the nth column of the matrix A. And how will I update them? I will replace them specifically with this quantity over here. Okay, so you can compute the update to the necessary entries of the matrix A either by using this formula. So I is the identity matrix of the appropriate size, so it should be the same size as V sub k times V sub k conjugate or transpose, right? By the way, maybe we should, again, this is just the transpose if all of them are off real entries, right? And then V sub k times V sub k transpose is a square matrix. It's a square matrix of dimensions m minus k plus 1. All right? Because, yeah, you can do the matrix computations, right? V sub k, we mentioned this is a vector of size m minus k plus 1 by 1. Its transpose is of size 1 by m minus k plus 1. So it's going to be, or the product will be a square matrix of size m minus k plus 1 by m minus k plus 1, right? So here you're going to use the identity matrix of the same size. So that's going to be the identity matrix of m minus k plus 1 rows and columns. Then you multiply that to the previous value, right? Then that's going to be the updated value, right? So compute this product over here. This guy, the second factor, is your unupdated matrix. The product should be set to be the new value of the appropriate entries of the matrix A. Okay? And then after you have updated the matrix A, you need to take note of the matrix H sub k. The matrix H sub k will follow the following block form, right? So this is something familiar. You already computed it here before. So we said this matrix here will be m minus k plus 1 by m minus k plus 1, all right? But H sub k should always be m by m. So you just fill in all diagonal entries here by the appropriately sized identity matrix. Here, the appropriate size of the identity matrix is k minus 1 by k minus 1, all right? So, because the total dimension of H sub k should be m by m. This guy will already take care of the m minus k plus 1 rows and the m minus k plus 1 columns. So I still need additional k minus 1 rows and additional k minus 1 columns to fill up for H sub k to be m by m, right? So this should be appropriately sized. Oh, let me check that. Should that be k minus 1 by k minus 1? And then everything else will be 0. Yeah, I think so. We can verify it further with an example later. So yeah, thank you, Lynette. Okay, and then now, so the result here is step by step, we are triangularizing the matrix A. So if you will, at every iteration, if you will ask your program to output the current iterate after every step in the for loop, the matrix A step by step becomes an upper right triangular matrix, right? But behind the process, we are orthogonalizing it. How are we orthogonalizing it? with the help of the unitary matrix Q. The unitary matrix Q will be this matrix. You get the product of H sub n times H sub n minus 1 until you reach H sub 1. Whatever the product is, we get its transpose or its conjugate transpose if you have complex entries, and that's going to be the unitary matrix. Okay? So I hope the process is making sense. There's a lot of formulas here, but of course you don't need to memorize them. We'll just encode this into a computer and they will just give us Q&A, right? It's as if it's another black box that will just rely on to give us the matrix Q&A, right? So let's see how this works, at least so that you can program it on your own later. And this is this is one thing I do whenever I'm having difficulties understanding the entire process and writing it in a code. Before I go ahead into encoding whatever the algorithm is, I start by doing a pen and paper computation so that I'll get acquainted to the intricacies of the method. So I'll be able to program it later, right? So let's see. I have here a small matrix, a 4x3 matrix, and I want to use householder's method in order to find a QR decomposition for it, right? So it's 4x3, so our m is equal to 4 or n is equal to 3. Algorithm says we iterate with a variable k starting from 1 until the number of columns. So I'll do k equals 1, k equals 2 until k equals 3, right? When k equals 1, the first step, you form the vector y. The vector y will be a truncation of the matrix A, starting from the first to the fourth column. First to the fourth row, but you'll use the first column. So that means first column, first to the fourth row. There we go. That's my matrix Y. The first entry will be our Y sub 1. Okay? Easy, right? Number 2, we compute two vectors, W and V sub 1. W follows this quick formula. So I have Y here. Since Y is negative, so I'll have a negative multiplier here. The norm of Y is actually equal to 1 because this is 1 plus 1 plus 1 plus 1, 4. Square root of 4 is 2. So that's where the 2 came from. The L2 norm of this guy is, the L2 norm of Y is equal to 2. So you can verify it easily. And then E sub 1 is the elementary vector of the same size as Y, but with 1 as first entry, but zeros elsewhere. That's how you got that 1, 0, 0, 0. That's your E1. And then perform the arithmetic, you're going to get this vector. That's our vector W. If you compute for the size or the L2 norm of the vector W, it is not equal to 1, so it's not unit, so we need to normalize it, right? So you compute for the size of this matrix with respect to the L2 norm, that's square root of 12. So what I'll do, I'll multiply the matrix W by 1 over the size of W, and that's going to be my V1. Okay? Yes. Yes, what's your question? Sorry, I forgot your name.
Steven
Yeah, Steven.
Miles.
Yeah.
Yeah, and to in number 2 there, I'm actually trying to see how you got the 2. Yeah.
Okay.
Exactly
sure.
what you.
Yeah, 2 here is the norm of the matrix, the vector Y. So basically, this is the square root of the sum of the squares of the entries. So -1, quantity squared, that's going to be 1, plus 1 squared, that's another 1. -1 squared is another 1. 1 squared is another 1. So that's going to be square root of 4, which is equal to 2, right? So again, remember, maybe we should put a note here.
All right, thank you. I got it. Thank you.
All right, good. So the norm of Y, or the L2 norm of Y, is the square root of the summation of all the entries in Y squared. Okay? All right. So, okay. And then essentially that's the same way how I got the square root of 12 for the norm of W. Okay. And here's the matrix V1. course, you can have the decimal representation for it. So that's your two important vectors, W and V1. Actually, I'll just use the vector V1 in all of the computations that will follow. All right. Third step, update the matrix A. Now again, since we are on the first step, we will be updating all the rows and all the columns, right? Because the update is from K to M and K to N. So I'll be updating everything via this formula. So compute this. So you have V1. You can just ask your code to multiply this guy by its transpose, then follow the formula, okay, and then multiply it to the matrix A, or the matrix that you're trying to update. Since here we are on the first step, we are updating everything, and here's what you get as your product. Okay, and you see here that at this very first step, we have a nice form. So we will not be touching the first row and the first column in succeeding computations because they are already following a rectangular form, or sorry, a right upper triangular form, right? Because everything below the main diagonal entry is already a 0. Okay. And then the fourth step, I will save as H1 this matrix. This matrix. Now, I minus, let me just copy the formula here so that we can discuss it easily. Okay, copy. All right, so this is the formula for H sub 1 in general. So for H. Now, I'm VK star in this particular case. VK is what? The size of VK is 4 by 1. So VK is 4 by 1. And then V sub K star is 1 by 4. So their product's going to be 4 by 4. 4 by 4 identity minus a 4 by 4 matrix is still 4 by 4. So this guy alone is already 4 by 4, right? Remember, H sub K was said to be always M by M. So I already have this component already occupies 4 rows and 4 columns. I'm expecting H sub K to only comprise of 4 rows and 4 columns. So I don't need to add this extra numbers here. So my H sub 1 will be entirely this guy. If you compute it, you should retrieve this matrix. Okay. Now, I want you to try computing this on your own later and see how that really this block here is exactly this matrix H1. Again, it's already 4 by 4. We are expecting H1 to be 4 by 4, so we don't need to add an identity and zeros there. Okay. Now we'll see the next case wherein we need to add something. All right. So let's go to the second iteration unless you have questions. For the second iteration, again, I will not touch the first and the first column because they are of the right form already, right? So here I am just updating, or we want to update the second to the fourth row and the second to the third column, right? So we start with the vector Y consisting of the entries in A occurring from the second to the fourth row, but on the second column, right? And you need to harvest this from the updated matrix A. If you're gonna go to the updated matrix A, so yeah, I forgot to mention that in the statement of the algorithm, you always go to the updated matrix A. So this is our new matrix A, okay? And then you will harvest second row to the fourth column. Second to the fourth row, second column. So that's gonna be this vector, right? So that's gonna be my Y in the second iteration, right? So that's gonna be my Y now. And now it's smaller. It's just a 3 by 1 matrix as we expected, right? First entry, 4/3 gonna be my Y sub 1. But actually all that matters would be the sign of Y sub 1, right? It's if it's either positive or negative. Second step, compute for the unit vector that is needed in the updating, right? So this is the formula. Again, you copy y over there, and then the sign of y1. Y1 is positive 4/3, so you get a positive there. Yes, Jehan, you have a question?
Yes, sir. For item number 1, Y sub 1 is the first entry. What if, for example, we have a 3 by 2 matrix? So Y sub 1 would always be the Y sub 1 entry, the
Uh,
first row, first column.
no, will only have one column every time. Because remember, in the algorithm, let's see, the formula for y is it's what? It's from the kth to the mth row, but just the kth column. So there will always be one column with lots of rows. All right. So yeah, it will just be a vector. I'm referring to it a matrix to be more general, but it's really a vector. All right. So yeah, yeah. I hope that that clears the confusion. Okay. And then yeah, so just copy y. 4/3 is positive, so that's why I get a positive sign over there. The norm of y, that will be again 2 incidentally. I hope I got the arithmetic correct there. And then this is E1, right? The same size as Y, but with 1 in the first entry and 0 all the way down. You're going to get your matrix, your vector W, and then you normalize it again, meaning you divide it by its size. So the size is what? I think the size of that matrix is 2/3 square root of 30. So you divide that, you get the reciprocal, you multiply that to y, and then you will get this guy, which is a nice round number, all right? So that's our v sub 2, and this is important for the update, right? Again, we go back to the matrix A that we have from the previous iteration. We already updated the first row and the first column, so we won't update them anymore. So I will just update the second to the fourth row and the second to the third column using this formula. This guy, I minus 2v2 v2 conjugate. If you want your code to be more efficient, or I mean, in terms of memory allocation, you can save this this value over here because you're gonna need this for what? You will need that for the matrix H. Okay, so that will be important later. So you can save this, multiply it to the parts that you want to be updated. You're gonna get this guy, and you will replace or you will update your matrix A with that. Remember, in the matrix A, we already said these are already updated. So you will just insert whatever this guy is to your current matrix A. And you see again, this is getting closer and closer to a right triangular form because you look at the entries below the main diagonal. They are already zeros, right? So that means we're fine with the second column and the second row. It's time to update the third row and the third column, all right? But the promise of this orthogonal triangularization is that we only do as much iterations as the number of columns. So that means we only have 3 columns, so there's only 1 iteration left. And we only, and that makes sense because this is the only guys that I need to update now, right? But before going to the third iteration, I need to take care of the matrix H2, or I need to take note of the matrix H sub 2. The matrix H sub 2 again should be 4 by 4. It should be a 4 by 4 matrix, right? But I minus 2 V2 V2 star. What is V2 again? V2 is 3 by 1. V2 star will then be 1 by 3. So their product would be 3 by 3. So this guy is a 3 by 3 matrix. So it's a 3 by 3 matrix, and actually that matrix is equal to this guy, right? So this is your I minus 2v2 v2 star, right? But I need H2 to be 4 by 4. So that's why I will insert an identity matrix, a 1-by-1 identity matrix, because this is already 3-by-3. So I lack 1 row and 1 column. So this guy, this block will be a 1-by-1 identity matrix. So that will just consist of 1. And then everything here will be zeros. That will be our matrix H2. Okay. And then finally, third iteration, k equals 3. I will harvest the third to the fourth row and the third column, right? So again, these are just the parts that we want to get updated. So we said these are unupdated yet. So I will harvest them. This is going to be my matrix, my vector y. Okay. That's your vector y, y sub 1. So typo, this should be y sub 1, 16/5. But we don't care about that value. We just need to harvest the sign, right? So y sub 1, you compute for its length or its size. It is 4. Then this is positive, so you get the positive sign over there. And then this is e sub 1, the 2-by-1 elementary vector. So 1 as first entry and 0 all the way down. Compute for w, you're going to get this. You compute the norm of v3. It's not equal to 1, so we need to normalize it. Doing this, getting this product will give us this matrix over here. Okay. Again, this is an important ingredient to update the required rows and column, right? So in this particular case, we compute this guy. Since v3 is 2 rows by 1 column, so this would be 2-by-2, right? So 2-by-2 times 2-by-1, so we'll get a 2-by-1 matrix, which will be our update for our last update for the matrix A. And you see now that the matrix A is upper right triangular. Okay, because all numbers below the main diagonal are all equal to zeros. Okay. Now, but the problem is this is going to be our this will be our R, right? So we already triangularized the matrix A, but the orthogonalization actually happened in the background. So we'll go back and compute for H3 because this will be very important in order for us to build or assemble the matrix Q, right? Remember, we have I minus 2 V3, V3 star. We said this is 2-by-2, all right? So 2-by-2, so this is actually that matrix. So I need 2 rows and 2 columns, right? So this is your identity I1. That's the required identity matrix. Then you put zeros on the other blocks. So it's important this is an identity matrix and these are all zeros. And then the matrix Q will be the product in decreasing index. So starting from H3, then H2, and then H1. Then you get the product, you get this, but you need to take its conjugate transpose. You will get this guy. And this is guaranteed to be unitary. Meaning if you multiply Q with its transpose, you'll get the identity matrix, which will be the same when you multiply Q transpose with Q. So it's going to be an identity matrix. Okay. And our right triangular matrix is this guy, which we already computed before. Oh, yeah, I already forgot about this, but the module says I have a MATLAB code for this. So for those using MATLAB, probably I can share with you the code that I used to implement algorithm tree or the householder algorithm so that you can play with it and see how the QR decomposition was done, right? So yeah, let me see what else is in here. Actually, if you're patient enough, you can just retype everything here. This is actually the MATLAB code I have for the householder algorithm. All you need to do is change this this line, right? So you need to type in your your input matrix over here, and then you'll ask MATLAB to do all the magic for you, right? So it will display the matrix Q and the matrix R. and this will be the output. So this is the unitary matrix Q, and this is the right upper triangular matrix R. Okay. And thankfully, I think I have here nearly exact answers, because you see that up to 4 decimal digits, they coincide with the values of Q and R that I computed earlier. Yes, Z, you have a question?
Yes, sir. Does this code accept any dimension of matrix by
Yes.
n?
Yeah, as long as
Yes.
your RAM can handle it, that's fine. Any dimension of the matrix will do. Because again, any matrix will have a QR decomposition. Let me just double check if this will allow. Oops. Yeah, I think it will also allow matrices with complex entries. So you can play with the code, and then you will see the difference between A conjugate and A transpose, right? Now, I am using them interchangeably because I'm assuming that A is a matrix with real entries. But when you have complex numbers involved, it will be a little different, right? Because you need to find the conjugate of the transpose before doing the unitary thing. Okay. All right. So I think the next step here is to see how we can employ the QR factorization in solving matrices, matrix equations. So we start with, and this will address one of our concerns when we started our talk about linear algebra, that how do we solve very tall and thin matrices? Because those are usually the case for data science problems. Because the number of rows often represent the number of observation or data that you have, while the number of columns represent the degrees of freedom or the parameters in a model that you want to construct using machine learning or deep learning algorithms, right? How do we solve how do we solve tall and thin system of equations, right? Now we'll still do the thing. So we're gonna start with AX equals B. A now is M by N. Of course, your method of doing A inverse times B won't work because we are sure that A is non-invertible because it is not square whenever M is not equal to N. Right? So now, how do we do this? Well, you run the code or you do the householder algorithm by hand. You can write A as Q times R. Again, we'll take advantage. What I'll do next, instead of taking advantage of the reflexive actually, yes, I can. I'm thinking of an alternative solution, but let me follow what's on the slides. Right? So you replace A by Q times R. Then you use the multiplication property of equality. You multiply both sides by the conjugate transpose of Q. To the left, remember, whenever doing matrix multiplication, the direction matters. So I will multiply both sides from the left by Q conjugate, all right? Or Q transpose, whenever you have matrices of purely real entries. And then I'll take advantage of the distributive property of matrix multiplication. Instead of grouping Q and R together, I will group Q conjugate and Q together. The reason why I want to do that, because Q is unitary. Remember, Q conjugate is also the inverse of Q. So Q conjugate times Q is just the identity matrix. So that means instead of solving equation 67, which is AX equals B, I can solve for equation 68 because they are equivalent, right? So here I have the matrix Rx times Q conjugate times B. There's no problem computing for Q conjugate transpose because it's just reversing the order, reversing the row number and the column number, then multiplying it to B, that's fine. Now, another nice thing about equation 68, the right-hand side has a right upper triangular form. Since it has a right upper triangular form, then you can do back substitution now. Okay? Any problems so far? Is everything good? Maybe, again, this will be much more clearer if you try solving problems on your own. Okay. Now let's look at a specific example here. I'll skip example 67, the example that I want, let me see. Because the example 67, I think will make use of the Gram-Schmidt process, which I mentioned to you will be very ill-conditioned or very numerically unstable. But if you're wondering what is really the effect of the numerical instability that I keep on blabbering about since day one, right? So if you have equation 69, the actual solution is -6, 11, and 2, right? So x1 equals -6, x2 equals 11, and x3 equals -2. Now, if you do QR decomposition using the classical Gram-Schmidt process, so you do everything, this will be the Q that you'll get, this will be the R that you will get, then you'll get this system, which you can do backward substitution on. And look at the solution that I got. The solution from the classical Gram-Schmidt QR factorization is this guy. But remember what the exact solution is? The exact solution is -6, 11, -2. Look at the answer we got from the classical method. It's nowhere near -6 to -11, or whatever the right answer was, right? And again, the thing here is not the QR decomposition doesn't work. It's just because when I ask MATLAB to do the QR factorization for me, following the Gram-Schmidt process, all those truncations inside the computer ruined the solution, right? So there should be no theoretical error because I'm not doing any approximation here. But the fact that I ask a finite machine to do the computations for me ruined the whole process, because now the error is 367%. All right, or actually, the size, not the relative error, but the size of the error is 3.6686, which is quite huge, right? Now, if I use the householder method, which I insisted on discussing, or I insisted on just discussing the householder QR factorization because I expect you to do machine calculations all the time. So if you run the code that I gave you, this is the Q that you will get. This is the R that you'll get. Of course, there is some more decimal digits stored inside my computer, depending on my settings when I use MATLAB. But this is the representation up to 4 decimal digits. And then I'll perform the process I mentioned to you earlier, and the same process that was done, the forward and the backward, the backward substitution that was also done from the result using the classical Gram-Schmidt QR factorization. And this is what I got. -6, 11, -2, which is precise up to 4 decimal digits at least when I compare it to the true answer, right? Now, the thing here again is not that theoretically the classical Gram-Schmidt is inferior to Householder's method. They are equivalent methods, but the problem is once you ask a computer to do the classical Gram-Schmidt process for you, the truncation error from the very finite nature of computers will kick in. It will overpower whatever theoretical accuracy that you maintain, right? But here you see, it's very close to the answer, right? When I compute for the percent error, so I'll get whatever solution I computed minus the actual solution minus the size of over the size of the actual solution. I'll get a relative error of 1.56 times 10 to the -16. And remember, whenever doing computers on IEEE standard computers, which is usually all your Intel products, they always follow the IEEE standard. Anything that is of order 10 to the -16 is virtually zero, right? So essentially, I have virtually 0% error for the solution I got from the householder method. Okay. Now, let's see. And then another example is from example 68. So I have here the matrix that we played with earlier in our hand implementation of the householder algorithm. This is rectangular again, so we don't expect the matrix inversion method to work even if it's a small system. This is non-invertible, but can we get a solution? That's the question, right? Now, if I use the right-hand side vector 2, 4, 6, 1, and I'll try to solve equation 70, I will see, of course, I cannot use A inverse because it doesn't exist. Now I'll use QR decomposition. Okay, so this is the Q and the R that we got, and then I will replace A by Q times R, do the thing that we mentioned earlier. What I'll get is this system. Rx equals Q star B, which is essentially this guy, right? Upper right triangular, your unknown vector, and Q transpose times B. If I translate it into a system of equations, I'll get 0 equals negative 3.5, which we know to be absurd, right? This is a contradiction. So that means there is no exact solution to this problem, right? Because if you will browse back, I already noted above, if you're if you're a theoretical, if you're good at linear algebra, you will see that the vector 2, 4, 6, 1 is not in the range of the matrix A. But if you forgot already what's the range of a matrix, just forget about it. The thing that's important here is that we get a contradiction in the last equation. So that tells us there is no solution, or at least there is no exact solution to this problem, right? Because it's inconsistent. Unlike the previous example that we have a unique solution. So whenever you don't have an exact solution, we look for the next best thing. What would be x1 and x2 and x3 that will make the equation AX approximately equal to B? When can we get when can we make AX approximately equal to B? Because that's the best thing that we can do, right? We want to get x1, x2, and x3 such that the product of the matrix A and X, that triple of constants, is close enough to 2, 4, 6, and 1, right? Because we don't have an exact solution. Well, QR factorization will give us a good guess for that, all right? So just never mind about the absurdity of the last equation. You do backward substitution in the first three equations, and the solution that you'll get is this guy, right? Which is not that good. Why? Well, if we compute A times the solution that we got, I called it X sub house here to stand for the solution from the householder method, we will get 3, 3, 3.5, 3.5. But remember, our target here should be 2, 4, 6, 1. But again, we know that that's impossible to happen. The best QR factorization can give us is 3, 3, 3.5, 3.5, right? Well, how good is that? All right. So, well, we get the size of the discrepancy between AX and the target, right? So this is what we got. Our target is 2, 4, 6, 1. Get their difference, get the size of that difference, divide it by the size of our target, you get the percent error. And the percent error is more than 50%. So this is the best solution we can get from the QR factorization, because householder's method is one of the best QR factorizers out there with respect to the L2 norm. But it can only give us accuracy of up to 50%. The next question is this the best we can do? Actually, it is not. We can push it a little better by solving the least squares problem. All right. Now, how do we solve the least squares problem? Maybe that will be a topic for next time. Or maybe I could, let me see. I still have 10 minutes left. So the best solution that we can get with respect to the L2 norm is what we call the solutions to the normal equation. Right? So remember, you start with a rectangular system, AX equals B, right? And then we multiply both, to get the normal equation, we simply multiply both sides by the conjugate of A, right? Which is valid per the multiplication property of equality. We will get this guy, all right? And then most of the times, if not always, this guy is always invertible, all right? Because even if A is m by n, its conjugate transpose will be n by m. When you take the product, it's going to be m by m. And often this is invertible. So there will be an inverse for A star A, right? So that means we can solve for x by multiplying both sides by the inverse of A conjugate transpose times A. So it's going to be A transpose A inverse A transpose B. And this is what we call the normal solution. The normal solution is the solution to the least squares problem, right? And if you do this computation, all right, you'll get this as our solution, right? So if you will just compute this in our instant problem, you will get, where is that number? There. You will get this as your solution, which is very different from what we got from the householder method. Yeah, I remember this guy. Whenever you're doing your computations in MATLAB, if you already defined what the matrix A is and what the vector B is for your problem, there's a one-liner solution to get the normal solution for the rectangular system. All you need to do is to type this exactly in MATLAB, and it will give you this guy, the least square solution. So it is guaranteed that this is the best that we can do with respect to the L2 relative error, right? But how good is this as a solution? Well, it's about 46% accurate. And you see, it's not that far from the householder solution that we got. Remember the relative error from the householder algorithm or the householder QR factorization is a little over 50%. This guy is over 46%. So it's just a 4% difference, right? So the normal solution is very tied up to the concept of the pseudo inverse. And if we have time, I don't know if I'll still be your teacher next week. We'll talk about the pseudo inverse, and that will be a nice time to wrap up our discussion about possible linear algebra tools that will help you with data science problems, right? Okay, so I think I'll stop here unless you guys have questions. Right, so I have a special guest here. We have Dean Zomer here. Hello, sir.
Hello, I just want to ask, how's your first problem set, the dashboard? I'm supposed to give Christian a sample, no, how to prepare the data set, but I think there's not enough time today. I can just record a video, but the prerequisite is you need to download R Studio. Okay, so I'm going to use R Studio to prepare the data set. But are there questions about that? Yeah. Okay, Steven.
Yes, sir. And I think where you come in, that's where I've been having problem on the problem set. The data, because the data is so large, we cannot upload in the Google Google Studio.
Yeah.
So
Okay.
because yes, yeah, it's very large. I think I had 290 from what I took from the site. From what I downloaded, it was too large, so it couldn't upload. So that the cleaning of that data set now, that's where I am, because I think you ought to clean it so that the capacity can reduce. Then it will easily upload in the Google Studio. So
Yeah.
I think
Okay.
that's where I am. So that particular area, that's where I got stuck from.
Yeah.
Yes, sir.
Aside from having very big data set, definitely probably my video later that I will upload about how to reduce the size of the data set. Other than that issue, are there other issues that you've encountered?
Yes, sir.
Go, Peter.
Yes, I learned that of the data set, I think around 4 to 5 of them actually are to be used. But like Stevie said, the issue of the cleaning, where to take those gaps from within it and to work with it in our programming. That's where the problem lies.
Okay, yeah.
Yeah.
Okay, so I think most of you, the problem is about the preparation of the data set. So I'll upload the video, but I think for now, please download RStudio. Please install RStudio. Okay? Thank you. I'll give back the Zoom to Sir Neil.
Yes, sir.
Thank you, Sir John. Okay, so I think we're all set. I think you're still busy with the problem set from Sir Jomar. So I'll probably, what? Do we defer our problem set or what? Well, maybe it will just be a quick problem set. I'll just ask you to say, to play with the MATLAB code that I will give you, right? Or if you can translate it to another programming language, then that's fine. So yeah, okay, I'll decide now to give it to you probably by Thursday. And then it will just be quick. I just want you to experience QR decomposition, explore some special cases wherein you will see that outstandingly the effects of machine computations to seemingly easy problems is not that given. So we need to take a look at them. And yeah, probably it will take you probably 1 or 2 days, but I'll keep the deadline probably a week after the deadline of Sir Jomar's problem set, maybe first week of April, right? Because your deadline is March 30th. So my deadline would be April, probably April 7 or something. I'll let you know on Thursday what I finally decide on the dates, right? So with that, thank you
Yes,
guys for coming today. Yeah, other concerns? None? So thank you for coming today. Have a good night,
Sir?
everybody. See you on Thursday. Oh, yes.
Yes, sir. I want to know where did you send the recording for last class?
Oh, yeah, I think I forgot to upload it. So what I'll do is probably I'll just drive home and probably right before midnight tonight, I'll post the recording of last week's session in the AMAT 255 website. So go again to section to unit 2B, scroll a little bit down, you will see a section on class recordings. I'll put the recordings there, right? Because I'm recording on my personal computer because so that Zoom cannot delete it after some days. So we will still have access to it even after the course. All right.
Okay, sir. Thank you.
All right. Thank you, everyone. Bye.
Thank you, sir.
All right.
Thank you, sir.
thank you, sir.
All right.